Hello. This lecture will cover pages 173 through 180 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on flip-flops and related devices, Part E, the JK flip-flop and its applications. Starting on page 173, the last flip-flop we're going to mention, the most important by far, is the JK flip-flop. It's used in many applications. You'll see some of those applications in a minute. The JK flip-flop is the most versatile of all the flip-flops. Therefore, it is referred to as the universal flip-flop. The internal circuitry for the edge-triggered JK flip-flop, I'd like you to go ahead and read this and look at this circuit. Make sure you understand the pulse steering circuit. Make sure you understand the edge detector. We've talked about that a number of times, how it enables gates 1 and 2. And I drew in the asynchronous presets and the asynchronous clears, making these gates 3 and 4 both 3-input NAND gates. The logic symbol for the JK flip-flop is down here. Notice it's almost always a negative edge-triggered. This is almost always a negative edge-triggered device. It has asynchronous presets, like I said. It has an asynchronous clear. The truth table looks like this. Notice that things happen on the negative edge, so there's our negative edge for the clock. Let me move this up a little bit. There you go. Negative edge for the clock. When J is 0 and K is 0, that's a no change. So the output is just Q to the N. At Q to the N plus 1, your output is simply what it was on the previous clock pulse, which was the Q to the N output. When J is 0 and K is 1, the output is cleared. It's reset. When the J is a 1 and the K is a 0, the output is set. It's a 1. And because of this steering circuitry here, because of these feedback terms coming back, the 1-1 puts you in a toggle state. That is extremely useful. 1-1 will put you in a toggle state, and the output will be the bar of what the previous Q to the N input was. So the way you memorize this truth table, and you really do have to memorize it, is the J is like the set and the K is like the clear or the reset in our previous flip-flops. Just remember, the J does the setting, the K does the clearing. A 0 and a 0, they're both inactive, that's no change. Here, K is active, so it resets the Q output. Here, J is active, it sets. And 1-1 will always give you a toggle. Take a look at example 5 on page 250. If you want to take a quick look at that, looks like this, depending on what version of the book you have. There's the problem 511. I don't know if you can read that, but there's the waveform coming in on a J input and a K input, and there's your negative edge triggered clock. I want you to see if you can reproduce that red waveform and see a T4, T5, and it's high, and at T6 it goes back to 0, and at T7 it stays at 0, and T8 it goes back high again. Just make sure you're able to reproduce that waveform, understanding how the JK flip-flop works. Then we're going to go to page number 74. On page number 74, below is a 4-bit shift register using JK flip-flops. Explain how it works. Just want you to take a look. Here's a 4-bit 4-bit shift register. Notice I'm taking the data comes in, and I'm making a D flip-flop out of the JK. How do I make a D flip-flop out of a JK? Well, the input goes to J, and remember, you invert it. You invert it and take it to the other input. That makes that just a delay flip-flop. And you don't need any more inverters as you go through here, because look what it's doing. It's taking the Q bar output. That acts as an inverter. You're taking the Q bar output and you're feeding it into the K, and the Q bar output and feeding into a K. So basically, you're taking the Q output to the J and the Q bar to the K on each case. And basically, that forms a shift register. You're using JK flip-flops connected like this. And if you take a look at your data in here, you can see that that data gets shifted at each clock pulse. Negative going clock edge, because these are negative edge triggered. Go through this and make sure you understand that. How would you build an 8-bit shift register? How would you build an 8-bit shift register using JK flip-flops? Just extend this on. Put 4 more on out the end here. Tie all your clocks together. On page 175, very important material we're getting into now, using JK flip-flops for frequency division and counting. This page you're going to have to look over a number of times. It's going to be very valuable for our design problems coming up the remaining of the semester here. But frequency division, divide by n counters. Mod n counters have n states and are divide by n frequency counters. Mod n counters can count up to n to the minus 1. What do I mean by all this? Let me be specific. And you sort of have to just memorize this as you go, and then once you do a few of these problems, you'll understand it very well, I'm sure. I've done this many, many years. Example of what I mean by this. A mod 8 counter has 8 states. When I say a mod 8 counter, I mean it has 8 states, and it is a divide by 8 frequency counter. A mod 8 counter can count up to 7 in base 10. What about a mod 12 counter? A mod 12 counter has 12 states. It's a divide by 12 frequency counter. The mod 12 counter can count up to 11 in base 10. What about a mod 24 counter? A mod 24 counter has 24 states, and it'll divide, and it is a divide by 24 frequency counter. The mod 24 counter can count up to 23 in base 10. I think you get the understanding here. Note, n-bit counters are not the same thing as mod n counters. Here's my explanation of that. If I have a 4-bit counter, it's not the same thing as a mod 4 counter. A 4-bit counter and a mod 4 counter are two different counters. A 4-bit counter needs 4 flip-flops, and it can count up to 15 in base 10. A mod 4 counter needs 2 flip-flops, and it can count up to 3 in base 10. Here's another example. An 8-bit counter is not the same thing as a mod 8 counter. An 8-bit counter needs 8 flip-flops, and it can count up to 255 in base 10. A mod 8 counter needs 3 flip-flops, and it can count up to 7 in base 10. Make sure you read this page over and make sure you can appreciate it, because you're going to need to understand this through a lot of the second half of the course. Page 76. Counter example. A mod 8 counter, as we know, has 8 states and is a divide by 8 frequency counter. Mod 8 counters can count up to 7 in base 10. So look what I'm doing here. This is a ripple counter. It's an asynchronous counter. We talked about them before. Here's my frequency coming in. The output goes to the input. Output goes to the input. Here's my least significant bit. And there's my next bit. Here's my most significant bit. This is my mod 8 counter, which has 3 bits in it. Here's my clock. 1 clock coming in. The clock just goes to 1 flip-flop in a ripple counter. There's my clock. I put an arrow on the negative transitions because this is a negative edge triggered here. And I do my timing diagram. Every time there's a toggle, Q0 goes. Just draw this in. Every time there's a clock, this becomes the clock to the next one. Put your negative edges on it. Q1 toggles every time there's an edge on that. These are easy to do once you see it. And then put a negative edge on that because it's negative edge out here. And Q2 changes on every negative edge. And notice, this is your 0 count. This is your 1 count. Here's your 2 count. Here's your 3 count. Here's your 4 count. Here's your 5 count. How am I getting out a 5 count right there? Well, you have a 0, 1, a 1, 0, 1, a 1, 0, 1. It's a 5. How's this being 6 out here? Well, it's a 0, 1, 1. 0, 1, 1. That's a binary 6. Notice it can only count up to 1, 1, 1. It can count up to 7. You get a 1, 1, and a 1. So it's only going to count up to 7 here. Then it starts over again, free running. We call that free running. Note, 8 states, and the frequency of the Q2 output is the frequency in divided by 8. Because this divides by 2, this divides by 2, and this divides by 2. I'm connecting these JK flip-flops as toggle flip-flops. How would I do that? J's a 1, K's a 1. J's a 1 and K's a 1. I'm just tying them to 1. And the way you'd actually do that, by the way, I'll let you put a 1 there and a 1 there. But the way you get that is you go through a pull-up resistor to VCC. That's the way you do that. You go through a pull-up resistor to VCC, and it puts a 1 there and it puts a 1 there. But I understand when you put a 1 there and a 1 there and a 1 there and a 1 there, you're doing this on each one of these. But if you make J a 1 and K a 1, look at the truth table we just covered for a JK flip-flop. That makes toggle flip-flops out of each one of these, and that's how that timing works. On page 177, how would we design a mod 6 counter, a divide by 6? How could we make the counter a mod 6? That's not a power of 2. It's easy to do a free running counter with a mod 4, a mod 2, or a mod 4, or a mod 8, or a mod 16. You just let it free run. But how could we design a mod 6 counter? What you do is you decode the 6th state. You look at this 6th state whenever Q is a 1, Q2 is a 1, and Q1 is a 1, and Q0 is a 0. You look for these two 1s. When Q2 is a 1, and Q1 is a 1, you want the output to go low. And you use that low true clear to clear all these flip-flops. You take that output right there whenever it sees the 6th state, and you make that 6th state the 0 state. And how do you do that? You decode the 6 with that NAND gate. How? You take Q2 and Q1. When this is a 1 and this is a 1, that's the first time this happens here. You want the output to go low. Why go low? Because these are low asynchronous clears. You just take this output right here and you take it to here, to here, and to here. And what that does is turn this mod 8 counter into a mod 6 counter. You count 0, 1, 2, 3, 4, 5. That's your 6 states. 1, 2, 3, 4, 5, 6. And when it tries to go into this 6th state, through a very small propagation delay, it's only in the 6th state for a prop time. One prop time until you clear this. So this 6th state becomes the 0 state. And it doesn't free run. It counts 0 through 5. And then 0 through 5. Show how you would modify the circuit at the top of the previous page to make it a mod 6 counter. Well, how would you do that? Go ahead and try that once. How would you make this a mod 6 counter? I just told you. You take Q2 and you take Q1, run it into a 2-input NAND gate, and out of that NAND gate, call it clear and take it here, here, and here. Page 178. I want you to take a minute on page 178, and I want you to show how you would design a mod 10 or a divide by 10 counter. It's not a free running counter. You're going to design a mod 10 counter. So you're going to decode the 10th state and make it the clear for all the flip-flops. So stop the video and see if you can't draw a mod 10 counter in by looking at the 2 previous pages. And see if you end up with what I got. Well, hopefully you stopped the video and you tried this on your own, because it's going to look awful easy when I do it. Unfortunately, when you get to the exam, I want you to know how to do this, so you're going to have to make up some of these on your own. Notice what I did here. Here's my least significant bit. Here's your clock coming in. It's a 4-bit ripple counter. If I free run it, it's going to count up to 15. It'll be a mod 16 counter if I free run it, but I don't let it free run. I decode the 10th state. Q3 and Q1. That's 10. That's 10. That's a 1, 0, 1, 0. When it sees this 1 and this 1 there, that goes low, and that low clears, asynchronously clears all these back to 0, 0, 0, 0, 0, 0. And you start up again until you get to the 10th state. It only has 10 states. It's a mod 10 counter. That's how you do it. On page 179, let me get this out of there. On page 179, state transition diagrams. I'm going to introduce them to you. They're pretty easy to understand. State transition diagrams are another way to represent how flip-flops change with each clock pulse. On a mod 8 free-running counter, here's the state diagram, the state transition diagram. It starts at 0, 0, 0, and every arrow represents a clock edge. First clock, it goes to state 0, 0, 1, and 0, 1, 0, then 0, 1, 1. It free runs the whole way through at each clock transition to a 1, 1, 1, and after 1, 1, 1, it's back to 0, 0, 0. How about a mod 6 state diagram, state transition diagram? That's what it looks like. Starts in 0, 0, 0 and progresses through 1, 0, 1. It's a mod 6. Mod 6 doesn't count up to 6. Look at that previous page. Mod 6 means it has 6 states. 1, 2, 3, 4, 5, 6, but it only counts up to 5. The mod number indicates the number of states in the counting sequence. What would be the state after 13 clock pulses to a mod 8 counter if it started in state 0, 0, 0? So just go up here to this mod 8 counter and start here and just count 13 clocks and see if you get a 5, 1, 0, 1. What if it started in state 5 and you got 13 clocks? What would it end up in? It would end up in state 2, 0, 1, 0. That's why, I mean, state transition diagrams are going to be extremely useful for you. And on page 180, it says N flip-flops connected as a free-running counter with no decode would have 2 to the n different states, and so it would be a mod 2 to the n counter, or a divide by 2 to the n counter, and it would count up to 2 to the n minus 1 in decimal. I think you already know that. We talked about it. Here's an example. Consider a binary counter that has 6 flip-flops and is free-running. Determine the counter's mod number. It would be a mod 64 counter. Determine the frequency of the output if the most significant bit. Determine the frequency at the output of the most significant bit if the input frequency is 1 megahertz on a mod 64 counter. Well, if you understood that one page, mod 64 counter just means it's just divide by 64. So the frequency of the most significant bit would be 15.625 kilohertz. What is the range of counting with both binary and decimal? Here's the range for binary, and the range for decimal is 0 is base 10 is less than or equal to the range, which has to be less than or equal to 63 in base 10. There's a lot of terminology I want you to understand in this lecture. So if you had any trouble with it, I really would like you to look this, let me see, this 19 minutes over again. And look at the lecture a second time. That concludes the lecture.